question 6, this question is about two experiments on gases. In the first experiment, liquid wire is injected into a sealed flask under vacuum. The liquid vaporizes in the flask. Table 2 shows data for this experiment. Calculate relative molecular mass of Y. Show you working. The gas constant R is 8.31 joules, K to the power minus 1, mol to the power minus 1. 5 marks. Classic question on ideal gas equation. And for these type of questions, when it's 5 marks, it's usually 5 marks because you're going to have to rearrange loads of units. You're going to have to convert units. So what we're trying to find? We're trying to find relative molecular mass. So we're not trying to find a mass, we're trying to find an MR. Right? How do you find MR? Well, moles. And so we're going to use the ideal gas equation, PV equals nRT. That's the first step. Then we're going to rearrange it while we're trying to find N, which is the number of moles. N is going to be PV divided by RT. Okay. What's P? Pressure. V is volume. R is gas constant R, and T is temperature. So pressure is in kilopascals. We want it in pascals in ideal gas equation. So it's going to be 51,000 pascals. Volume. Well, in the ideal gas equation, we want it in meters cubed, not moles per dm minus cube. So what we need to do is it's going to be 482 divided by a million, so times by 10 to the power minus 6. Temperature, that's already in its correct unit, 297 Kelvin. And sometimes they'll also keep one in its correct unit to try to trick you out. And then you think, oh, maybe we need to convert it to degrees Celsius. No, it's perfectly fine. And the mass of Y, well, that needs to be converted into grams. So we just divide by 1,000. So now we've got all these values. Let's substitute them in. Convert them. So it's going to be pressure 51,000 times by the volume divided by a million. So 482 times by 10 to the power minus 6, because we're dividing by a million, over R, which it gives us in question 8.31 in joules, times by temperature 297. Now that will give me the number of moles. Don't be fooled, that's not going to give us the answer. That will give me the number of moles. Now that will give me N, the number of moles, is 9.96 times by 10 to the power minus 3. We are trying to find the MR, the relative molecular mass, and we know moles is mass over MR. So therefore MR is going to be the mass. MR is going to be the mass in grams of Y, which we've already rearranged, which is going to be 0.717 divided by the number of moles, 9.96 times by 10 to the power minus 3. So 0.717 divided by my answer, and that will give me 71.987880504. Does it say round to any significant figures? No, it doesn't. However, we can round it to 72 to 2 significant figures. We don't need to say that. 72.0. Okay. So yeah, the hard part is there's only a couple of parts to it. You memorize the equation, which you should know by now, and rearrange it. So this I'm assuming you guys know how to do. The only hard part then is converting the units. So from milligrams to grams divided by 1,000. From Kelvin, well, Kelvin is already in its correct unit, but if we do need to convert it, let's say it gives its temperature in degrees Celsius. Well, to go from degrees Celsius to Kelvin, we just add 273, and to go from Kelvin to degrees Celsius, we minus 273. Volume, or centimeters cubed, obviously ideal gas equation, we want it meters cubed, so from centimeters cubed to meters cubed divided by a million, times by 10 to the power minus 6, and pressure from kilopascals to pascals, just times by 1,000. times by 10 to the power minus 6. And it is imperative that you learn how to convert between these units and you know them off by heart. And then 6.2, in the second experiment, another flask used for combustion reaction. Method: remove all the air from the flask, add 0.0010 moles of CH18 to the flask, add 0.0200 moles of oxygen to the flask, spark the mixture to ensure complete combustion. Cool the mixture to the original temperature. The equation is that. Calculate the moles of gas in the flask after the reaction. So, in the products. Now, I fall for this trap a lot. But because it says moles of gas, all we're looking at is this 8CO2. We don't care about this 9H2O because that's liquid, and that's where I struggle the most with these type of questions. But now I've made the mistake so many times and I've spotted it. I've learned from it. So yeah, that's the first thing. But now we know we're adding this much moles of this, 0.0010, and we're also adding this much moles of this to the flask. So how do we find out the moles of gas in the flask after reaction? Well, it's a 1 to 12.5 ratio, and if we have this much moles of CH18, how much should we have of the oxygen? Well, it should be 0.0010 times by 12.5, which is 0.0125. How much moles of oxygen is actually added? 0.0200. So we're going to do 0.0200 minus 0.0125 to give me 0.0075, 7.5 times by 10 to the power minus 3 moles of O2. Now we want to find out the moles of CO2. Well, the moles of CO2 is just going to be also 1 to 8 ratio. So it's just going to be 0.0100 times by 8. 0.0010 times by 8, which will give me 0.008 of CO2. So we've got O2, CO2 in the flask after reaction, 0.0075 plus 0.008, 0.0155 moles. And that is the end to question 6.